Hello, everyone. It's my pleasure to introduce to you Connor Bottrell. He's an expert in galaxy formation and the connection between simulations and observations, but I'm not going to talk more about that because that's his job. A little bit about Connor's background. He did a PhD at the University of Victoria with Luc Simard and Sarah Ellison. During that time, he also spent quite a bit of time here at UDM, so some of you may already know him. So that's cool. Now he's doing a postdoctoral fellowship at the Kavli Institute, the IPMU Institute for the Physics and Mathematics of the Universe at the University of Tokyo, where he also holds an NSERC postdoctoral fellowship. Now he's actually just accepted a forest fellowship at ICRAR in Australia. So he'll be going there this summer for his second postdoc. And with that, I guess I'll leave it to Connor.
Thanks very much. Yeah, hopefully not. Hopefully the second and last, and not the second of many more. So yeah, hello everyone. My name is Connor Bottrell. It's a real pleasure to be here, and it's, trust me, it's been a real pleasure chatting with many of you over the last couple of days, and I look forward to future chats, including today and tomorrow. So yeah, I still have an open schedule tomorrow afternoon. So if anyone wants to talk about their work and about galaxies or synthetic observations, I'd love to chat. So yeah, that said, the theme of what I'm going to talk about today is how we can use the forward modeling of galaxies from numerical simulations to inform observations, right? So I'm seeking to understand how we can connect the observable properties of galaxies that are produced through such forward modeling methods to their intrinsically unobservable properties. These mappings can only really be done using simulations. So I'm going to start by asking you, and I'm going to, don't cry out, but start by asking you which of these galaxies are real and which of these galaxies are not real. Right? All of them have fairly realistic morphologies. You have galaxies with spiral arms. You have galaxies which are the centers of very large clusters, which have shells, which are remnants of dynamical interactions between other galaxies and the center of that galaxy's potential. You have similarly have stuff like this, where you also have these shells, but then these large prominences, which are associated with a galaxy ramming through the center of potential at very high speed, so very low impact parameter, very high velocity merger. And otherwise, you just have the nice diversity of morphologies. So the thing that I'm going to focus on the talk today is this forward modeling process. And this forward modeling process allows you to do three very important things. Taking galaxies from hydrodynamical simulations in which you model the evolution of gas, stars, and dark matter through cosmic time from in cosmological initial conditions up until now, allows you to compare in an apples to apples way simulations and observations in the same domain, using the same tools as you use in observations. Right? The other thing that it allows you to do is allows you to infer how the observable characteristics of galaxies came about. What are their origins? What sort of assembly histories give rise to certain properties? How is the assembly history of this galaxy different, for example, from this galaxy? This is something that you can only do within simulations. So this is the inference. But then there's an even more interesting and the most interesting thing you could do is you can construct mappings between the synthetic observables and these intrinsically non-observable properties. For example, you may want to know what are the constituent galaxies that over time that ended up forming this galaxy. You have many mergers between smaller galaxies that form larger galaxies. And so how does the assembly history of this galaxy differ from this? This sort of mapping can only be created using highly nonlinear models because it is a highly nonlinear function. And so by using deep learning and forward modeling and hydrodynamical simulations, we can establish these mappings and then apply them to real observations where we are most interested in being able to make these measurements and inferences. All right, so we live in a hierarchical universe. In this universe, large structures such as this are formed through the hierarchical assembly of smaller structures, but that is the story for dark matter. The story for the stellar material within those structures, that is, the galaxies themselves, the story is a bit different. In that sense, there is this competition. It is not just through hierarchical assembly, although there is an assembly component, which is this ex situ acquisition of stellar material from other galaxies. So that is, you have other galaxies that are giving their stars to the galaxies in mergers, essentially. And then you have the in situ formation of stars within galaxies. And so this is the competition. So you have gas that is found within these galaxies, within these structures, and then that is converted into stars through star formation. And then you also have gas that is outside of these galaxies, which is accreting into these galaxies, which is subsequently turned into stars. So one thing that we would be very interested in being able to do observationally, which we don't have access to, is to be able to reconstruct what this assembly history looks like for an individual galaxy. So that is something that is the intrinsically non-observable part. On the other hand, what we can do is we can make forecasts. We can look at galaxies that exist right now, and we can assess how likely they are currently to merge for a given, for example, for mass, using spectroscopic surveys. In addition, their star formation rates. So we can examine this competition between in situ and ex situ stellar assembly explicitly using spectroscopic surveys, but only in the forecast sense. We're not able to look back in time and infer their histories. So in a spectroscopic survey, you have maybe 200 to 600,000 objects with spectra. For each of those spectra, you have which is planted on a galaxy, you can infer the stellar mass and the star formation rate based on spectral lines and the continuum emission from stars. So that's what gives you this curve here. So what you're looking at is the specific stellar mass gained versus as a function of the stellar mass of the galaxy. That is, relative to the galaxy's current stellar mass, how much more mass is it forming per year, right? And so that's what the blue curve is showing, is the in situ star formation just inferred from the star formation rates of galaxies. As galaxies get bigger, it is harder and harder to grow an appreciable amount of their mass just from in situ star formation. That is what the blue is. So you have this decline in the specific mass gained for in situ star formation. On the other hand, this red curve is showing the ex situ stellar assembly. That is the ex situ process acquisition of stars from other galaxies. How do you infer this? Well, this is the other beauty of spectroscopy. Because for a given galaxy, you have another galaxy which also has a spectrum. You can measure the angular offset between these two galaxies and corresponding physical offset. And then you can use their relative velocities from the spectra to infer with some dynamical accuracy whether they will merge within some appreciable time scale. And so using this merger rate and the merger fraction of galaxies, you can assess as a function of mass the amount of stellar material that is expected, forecasted, to be grown through stellar assembly, or through ex situ processes, through mergers. And so if you then take these two processes and you relativize them, that's what this is showing. This is a relative effect where one corresponds to an even combat between the star formation dominated growth and the merger dominated growth. You can see that low mass galaxies, their growth of stellar material is dominated by star formation. And for high mass galaxies, their growth of stellar material is dominated by mergers. And this makes very nice sense. And this is one of the great beauties of spectroscopic surveys. It very largely solved this problem, at least in terms of forecast. So at any given redshift, if you do this, you can predict the forecast of stellar assembly in galaxies. It's great. But that isn't really the whole story, because mergers also trigger star formation. So despite the fact that you have this sort of competition between in situ star formation and ex situ star formation, or stellar assembly, you also have the triggering of star formation intrinsically because of mergers. When you have a merger, such as this, you're starting out with this galaxy here, it joins maybe a small group at some point in time. So we're actually looking along this axis here, which is time relative to the merger itself, 0 corresponding to the point of coalescence. So this is in the pre-merger phase when you have two separate galaxies. And this is in the post-merger phase or post-coalescence phase when you have only a single galaxy. That's the remnant. And so starting out at point A, we have a nice cherry-picked spiral galaxy from this numerical theory of a galaxy merger. So you have on this axis the AGN luminosity, and on this axis the star formation rate. So we take this isolated disk galaxy, we at point A, it's merrily star forming, it has no real AGN activity. It joins a small group, it then begins to interact with the members of that group. And these interactions yield not only morphological changes in the galaxy, such as the ones you see here, bridges, tidal arms, streams, shells, all of these features that are intrinsic, well, mostly intrinsic to galaxy mergers. But it also yields internal physical properties, internal physical changes in the galaxy's properties, such as the star formation rate, where you see a little bit of a bump here, and a big bump in AGN luminosity. And that is because when you have a merger, you're not just changing the properties of the stars, but you're also creating torques on the gas disk in these gas disks in these galaxies, which drag angular momentum away from the gas into the orbital plane, where the gas can now accrete towards the center of the galaxy, where it compactifies, forms more stars, and also when the galaxy and the stars that do the gas that does not turn into stars can accrete onto the black hole and activate the active galactic nucleus around the supermassive black hole. And so this process that I've just described here in the sort of pre-merger phase or the pre-coalescence phase, this has also been very well characterized by spectroscopic surveys, right? Because whenever you have two individual galaxies separated by some space and some velocity, you can make a very pure spectroscopic cuts to say whether two galaxies are going to merge in the future, right? And so this is what that looks like. So on the lower panel, I'm showing you the x-axis, the projected separation between two galaxies each with their own spectra. And on the y-axis, I'm showing their star formation rates. Those are also inferred from the spectra. So for the merging galaxies are shown here in blue. So as you can see, as you go towards higher star formation rates, you have, as you go towards smaller projected separations, you get higher enhancements in star formation. So that it makes perfect sense. It fits perfectly well within the theoretical picture that we just painted. In the red, what I'm showing you are the statistical control galaxies. Now this is going to be a theme throughout the talk, so it's important that I lay it out now. So for each merging galaxy, you assign a statistical control galaxy, which is otherwise similar but is not merging, right? So you would find a galaxy which has the same mass, lives in the same environment, and is at the same redshift as your merging galaxy, but is just not a merger. So that just means that you're removing any correlations between these ancillary parameters. So we know, just based on the plot before, that there's a relationship between star formation rate and mass. So we're just making sure that we're comparing like with like, and so when we're checking for these enhancements. And sure enough, when you plot one against the other, or one over the other, star formation rate of controls, of mergers over the star formation rate of controls, you get this enhancement factor, which is reaches about a factor of 3 or 0.4 dex. All right, so as I said, this part of the sequence is very well characterized. You can do the same thing for AGN. It has been done. We see that AGN are also more frequent amongst mergers than they are amongst their statistical controls. Now, the tricky part is in this part of the sequence, right? Because now spectroscopic identification of mergers is out of the window. You can't use spectroscopy anymore because you now don't have two objects anymore. You have only a single object that you're looking at. So you can't use a relative velocity cut and angular separation cut in order to identify these things. You have to rely on the intrinsic and morphological properties of these galaxies to infer whether it's a merger or not. And that runs into the problem of ground truth. Because when spectroscopy, if you take a relative velocity offset, projected separation cut, based on the dynamical constraints, you can say with some percentage certainty that two galaxies are going to merge. But here you have no ground truth, no such ground truth to use. And so that makes it considerably tricky. And so this is why I have quite always strongly advocated for the use of simulations in order to inform us about what is ground truth in the case of what is a merger, what is a pre-merger, and what is a post-merger in this sense, and how to separate between post-merger galaxies and ordinary galaxies. And that is because in the simulations you have access to ground truth. So here what we're looking at is a recent merger remnant, but then we can just rewind time and find what its progenitors looked like. So we have access to this galaxy's full assembly history. And so this is from a cosmological hydrodynamical simulation called the TNG50 simulation. It's a 50 megaparsec volume that has been, or co-moving megaparsec volume that has been evolved from, redshift 128, so basically arbitrarily CMB-like initial conditions, and forward and explicitly modeled forward in time up into redshift 0. And so the great advantage is that we can take an individual galaxy at any point along the sequence. We can move forward in time and we can move backward in time to assess what its assembly forecast is and what its assembly history was, to get ground truth knowledge of these labels, where a galaxy is in its merger sequence. And this is what that looks like, at least for the assembly history. So taking a galaxy that looks like this, that is right here on this plot at redshift 0, and we're just moving down backward in time to what constituent galaxies form this galaxy over time, right? So this is half of the story, right? You have here the assembly history of stellar material from ex situ processes, but not in situ processes. So, but the big advantage here is that we have access to things that are intrinsically non-observable with the simulations. But and using certain techniques, we can map these intrinsically unobservable properties to observable properties. In order to do that, we need to create the synthetic observable properties, because in the simulations, what we have access to is particle information, just floats, float data. What we really want is something that looks exactly like what an observer would look like looking at a galaxy. And so this is the forward modeling process. So starting out with some set of floats, 6-dimensional like velocities and positional space, but also other properties of features of stars, such as their metallicities, ages, and masses. We assign spectral energy distributions to each stellar particle within the simulation based on their ages, masses, and metallicities. And then we propagate those through gas and dust, which we also put into the simulation, which are also included in the simulation, towards some camera that we put inside the simulation to reproduce what the galaxy would have looked like as if we had observed it with any arbitrary instrument. And so that's what you're seeing in the upper panel, row of panels here. So these are just 4 different line of sight orientations looking at an individual merger remnant. And then beyond this, so now we're now looking at the full merger sequence in sort of a loop. And beyond this, we can then take these idealized images, which are noiseless. They contain no artifacts of other galaxies which are in the foreground or the background. They only contain galaxies which are physically related to the ones that we've run through this forward modeling process. And then we take these noiseless images and we mock them up to make them look exactly like they would look like if we really did observe them with a telescope. And that's what's being shown here in the lower panel. The lower panel is taking each of these images and putting it into a real imaging field from a real survey. And we do this statistically to make sure that all of the biases are exactly matched in a statistical sense. So by taking a basis catalog of real galaxies, we draw the insertion statistics based on the positions of those galaxies in the basis catalog, such that you match the statistics for sky brightness, point spread function resolution, and crowding by nearby sources as they exist for real galaxies. So all the biases are identical. So this is quite useful. And it's quite useful because now we have this very nice mapping between the observable domain of these simulated galaxies and their merger histories or their merger stage. And we found that essentially that if you train nonlinear models, such as deep learning models, to predict what the merger stage of a galaxy is, you can do it extraordinarily well using these mappings. So we can split, for example, galaxies into the merger sequence into the pair phase and the post-merger phase, and we can use models like this to identify galaxies in that elusive post-merger phase where we don't have access to spectroscopy to identify galaxies. And so, as I said, in order to do this, this is a highly nonlinear mapping. So we need a highly nonlinear model in order to mitigate that, in order to facilitate that mapping. And so we use like visual cortex models, such as CNNs, in order to do this. So you have CNN is a convolutional neural network, is broadly divided into 2 components. You have the image-facing component or the data-facing component, which is, well, in general, they can deal with any type of data which exhibits some topological structure. But in this case, we're dealing with images. So you have a feature extraction component, which deals with which face the image and then create more and more abstract versions of the information encoded in that image and pass it further down the line until we get to the representation component. Now, I call this representation component. Many of you will probably be familiar with the classification component, but really, if you cut off this final classification layer, which decides whether the galaxy is a merger or not, or what stage of the merger it is in, what you end up with is just this vector. And that vector is really key, because that is the vector that encodes all of the information that is encapsulated in this image that is pertinent to the classification, right? And so that vector itself is extraordinarily useful, and I'll get into that in a little bit later. But for now, let's talk about some classifications. So we set out, we came up with this idea that we're going to use these hydrodynamical simulations and forward modeling and these deep learning models to train to calibrate some model which can identify post-merging galaxies, using ground truth labels from the simulations. And so that's what we did. So here we have 10,000 post-mergers. So this work was led by Bobby Bickley at the University of Victoria. And so we have 10,000 post-mergers, all satisfying some stellar mass ratio constraint. So stellar mass ratio is just the ratio of the masses between your primary galaxy and its companion in the merger. So it's 1 in 10 or greater. And then we also identify 10,000 controls. So these are, again, galaxies that have been matched in mass, environment, and redshift to our post-merger galaxies, so we don't allow the model to exploit some hidden correlation. We know that, for example, bigger galaxies have more mergers. So that is, more massive galaxies have mergers. And so if the model is just exploiting stellar mass in order to infer merger status, then that would be bad, right? So we don't allow that to happen by applying this control matching. So we use these images to train a CNN, and based on the simulations, we get about 90% accuracy. Now, that does not mean that the 90% accuracy exactly translates to observations, because there are intrinsic differences between galaxies from these simulations and the observations. That we cannot control. So what we gain in terms of ground truth, we lose in terms of the similarity of galaxies. We lose in terms of the fact that you're dealing with a different universe in the simulation than the real universe, slightly, right? Ideally. So then we applied this model to CFIS images nonetheless. So CFIS is a large imaging program. It's called the Canada-France Imaging Survey, operated with CFHT telescope. It gets about 2 magnitudes deeper than SDSS and at 0.6 arcsecond resolution. It's a very nice survey. Has images in the R band, which is what we applied our model to. So in the upper 2 rows, I'm showing you galaxies, real galaxies now, which scored highly according to the model. So these are all galaxies which are post-merger candidates according to our model. So, and all of them exhibit really clear features of mergers. Some of them are erroneous because you have some galaxies which are in the very, very close pair phase, but you'd expect that to go wrong in that area, because you have 2 separate nuclei. It's true. So it's not really a post-merger, but you have a lot of shared features between post-mergers, like really early post-mergers and really late pairs. So you do expect to go wrong in some cases in this case. So maybe some visual cleaning will have to be done. So in the lower panels, I'm showing you images of galaxies which scored very poorly according to the model for post-merger status. Now, what I want to draw your attention to is that all of these galaxies exhibit structure. That is really one of the key things of using these CNNs, because instead, if you use a different non-parametric morphology to assess whether a galaxy is a merger or not, such as the asymmetry. So in asymmetry, you take an image of a galaxy, you rotate it by 180 degrees, and you subtract it from itself. And so all of the structure that is left over is essentially asymmetric. But many galaxies are asymmetric. Any star-forming galaxy is asymmetric. So if you're using this, like asymmetry, for example, to characterize whether a galaxy is a merger or not, even though it might be quite complete, it'd be very impure because you'd be including just lots of star-forming galaxies. All right, so that was the advantage of the CNN approach. And so we then can look at the star formation characteristics of galaxies that are post-merger galaxies. That is what's being shown here. We're looking again at the median SFR enhancement amongst post-merger galaxies compared to controls. But here as a function of the cut used to define the post-merger sample, right? No worries. So we have some cut, which we use to define the post-merger samples. This is just the threshold above which we say, according to our probabilities, these galaxies are post-mergers, right? And so if you just use the CNN predictions, if you have to go up to an extraordinarily high probability in order to reach like a reasonably high level of enhancement, right? So we're sort of, so it's quite interesting. Even if you get up to maybe like 90%, you're only sitting at about a 0.1 dex enhancement in SFR, which is not consistent with what we see at the very late pair phase. Earlier I was showing you that it was about 0.3 dex or 0.4 dex enhancement in star formation rate amongst galaxies that are separated by 10 kiloparsecs. But that's not consistent with what we're seeing here, and we should expect to see a consistency along that with that very late pair phase, but we don't. So what we had to do is we had to take our candidate sample of post-mergers above some cut in post-merger probability and then visually clean it. As I mentioned, we had many galaxies which you had two separate nuclei, which were not really post-mergers, which are still late pair phase. But you also have systems which have stars within the field of view, which confuse the model, even though it has been exposed to stars in training. It's not perfect. And so you still have to visually prune the sample in order to produce a very pure sample of post-mergers. And so when you do that, you get the orange points here. And so there you get consistency with the pair phase. Now, this is a bit cheating, right? Because we started out with this idea that we could use a strictly quantitative approach to identify post-mergers, but now we have to go back to the subjective approach, right? But it is clear that the human knowledge component is important, right? By injecting our human knowledge of what is a post-merger and what is not into like a candidate sample of CNN, we have a candidate sample produced by the CNN, we get a big difference in the physical characteristics that are inferred, right? So we'll get into that in a moment, but here's one other thing. All right, so yes, we can see that mergers enhance star formation, but what about the suppression of star formation? Okay. You also see that there's a connection between the shutdown of star formation and the merger activity. So if you look, for example, at a bunch of galaxies that are suppressed in star formation, have no active star formation right now, these are called post-starburst galaxies. Galaxies that recently had a burst of star formation, but are no longer forming stars. And you can identify these galaxies by looking at their spectra, right? So if you look at the D4000 break and bluer, so 4000 angstrom and bluer, you can identify galaxies which are deficient in O and B stars. These stars are very short-lived, maybe 10 megayears, 10 to 100 megayears. If you see a deficit of these stars, then you can say that the galaxy was forming stars recently, because you still have A stars, for example, but is no longer forming stars actively. And you just have different methods of identifying these post-starburst galaxies, but that is just one. So you have two different ways of identifying post-starburst galaxies, and those are shown in the green and in the blue here as a function, again, of CNN prediction threshold, right? And so here we also have the controls. And so what we're looking for is the merger remnant fraction amongst those post-starburst galaxies. So how many post-starburst galaxies are actually merger remnants? And what we find is that as you increase the CNN prediction threshold, you have a significant enhancement or excess in the merger remnant fraction and amongst like post-starburst compared to controls. And we see that after visually pruning again, we see that reaches about 30% of post-starburst galaxies are merger remnants. That's quite interesting. So these mergers are driving the starbursts, which are then subsequently shutting down future star formation. That's the picture, at least for 30% of the cases. But again, this is still circular. We've set out with this idea that we're going to use a strictly quantitative approach, but we're having to go back to the human objective approach in order to do it. But it's clear that the human knowledge is important. So why not include that from the get-go, right? So this is a project that's being led by Kiyoaki Omori, who's a PhD candidate at Nagoya University, with some help from Mike Walmsley, who's going to be at U of T, at the Dunlap Institute very soon. So what we've done here is we've automated that human knowledge, right? So what Mike has done is he's taken 300,000 galaxies from the DECALS survey. This is nice, deep imaging of galaxies, all with spectra. And he's used the galaxy zoo vote fractions of these galaxies to train a model which creates representative representations of galaxy morphologies. So just a quick description of how that works. So for every galaxy in Galaxy Zoo, you have random citizens. So citizens like yourselves, or no, I mean, you're all astronomers. Sorry. So anyone can go through the Galaxy Zoo and classify galaxies. And they classify them according to this table, right? So is the galaxy smooth, or does it have features or a disk? And then there are subsequent questions such as, does the galaxy contain a bar? Is it a weak bar or a strong bar? How wound are the spiral arms? Does the galaxy have shifting isophotes if it's an elliptical galaxy? Does it have tidal features, et cetera, right? And so what Mike did is he used all of those classifications, the vote fractions in each of those, to optimize a model, which he called Zubot, to build representations of galaxy morphologies as the main product. So what essentially you get out is a meaningful representation of all of the information that is encoded in the image with respect to galaxy morphology, based on human knowledge, right? So that is the key. This is a human trained model. These weights, the weights of this model are essentially human eyes, right? And so what we end up with is this model, and we decided to then just very simply fine-tune that model to the new problem of identifying mergers. Because it's very easy to fine-tune this model, right? So with these, just to give a picture of what these representations look like, suppose that you find some galaxy in your data set that you're interested in. Well, because you have a representation vector, which comprises maybe 100 to 1,000 elements, element vector, you can just look in Cartesian coordinates, and compare the positions of galaxies in that representation space and identify a whole bunch of galaxies that look just like it. So suppose that I'm interested in identifying galaxies that have dust lanes, and I identify one galaxy that has dust lanes. Well, then I put this galaxy through the model, I build its representation vector, and I find nearest neighbors. And then I get a whole bunch of galaxies with dust lanes. And it's the same thing with the regular galaxies with the tidal features. This is just telling you that the representations built by these models are meaningful, right? And it's all done with human knowledge. The other really nice advantage of this model is that it allows you to fine-tune the model to a new problem and a new data set with very limited data, right? Because you already have pre-trained the model based on these 300,000 images and vote fractions from Galaxy Zoo. So in order to fine-tune it to optimal accuracy based on new data, you only need a very few samples. What you're looking at here is the mean accuracy of the model in a new challenge, something that the model was not not part of the classification scheme, whether galaxies have rings or not. So you say, I want to take this model, and I want to say, get this model to identify rings, right? Ring galaxies. So the blue curve, so you can ignore these other curves because they're just different models that exclude certain parts of the data. So the blue curve and the black curve are what I want you to focus on. So as a function of the number of ring galaxies required to train the model, what we're looking at is the mean accuracy, right? And so the blue curve uses the fiducial Zubot model. And after only 200 samples, so only 200 training images, the model is able to reach 85% accuracy. Whereas if you train from scratch, at 200 training image, you have 50% accuracy, or otherwise, flip of a coin. Whereas if you were to train with 10,000 images, yeah, maybe you reach about the same accuracy as you do with Zubot at 200 images. So this is enormously advantageous, right? Because now it means that we don't have to do too much expensive radiative transfer in order to train such a model, because this process of forward modeling from the simulations is actually very expensive because you're propagating, photons through gas and dust and scattering and absorbing. It's expensive. So we did do a little bit of that. And we built 1,000 images of galaxies in mergers from the TNG50 simulation, and we built a corresponding 1,000 images of non-mergers that are their statistical controls. And we use this to fine-tune Zubot and enable a transfer learning between decals and HSC. It's a different survey. The decals, HSC goes another magnitude deeper compared to decals. It's in 5 bands, 1,500 square degrees. And it has extraordinary resolution. It's an amazing survey. I highly encourage you to all look it up. It's a hypercram super strategic program. And so we used Zubot and we fine-tuned it on this very small sample of mergers and non-mergers and applied it to real HSC galaxies. And this is what you get. So these are galaxies which had low scores according to the model, and these are galaxies which had high scores according to the model. And so again, what you're seeing is that now when we started with human knowledge and we fine-tuned on the ground truth from simulations, we get a very similar results. We do see again that we are identifying bona fide mergers with high scores and non-mergers with low scores, but nonetheless structured. So then we can use this data set to assess where mergers are happening, right? So the thing that Kiyosaki wanted to tackle in this project was where mergers are happening in the universe, right? What environments are mergers happening in, right? Because intuitively, you would expect that mergers should be happening where there are a lot of galaxies, right? But that is not the case, actually, because what we're showing here is the cumulative fraction as a function of p mergers. These are just cumulative distributions. And so what we're plotting here is just the data as a function of p merger binned in different environments. So low density corresponding to blue, high densities corresponding to red. And what we see is that at higher p merger, galaxies at higher p merger tend to be concentrated at low density environments, whereas galaxies at low p merger tend to be concentrated at high density environments. That's exactly converse to what the intuition, and it's also converse to what you would infer from spectroscopy. But it's not converse to what you get from lambda CDM, right? Because in lambda CDM, if you just do an n-body simulation of galaxies and mergers, if you go into the high density clusters and high density groups, the velocity dispersions are so enormously high that you never actually have mergers between constituent galaxies. They're very rare. You do have mergers, but they're very rare. Whereas the field scale, the field and low density smaller groups, you have a higher frequency or a higher incidence of mergers in those environments. So because we are using a morphological model here, so strictly based on the inference of what merger status from images, we're not biased to interlopers when you're dealing with spectroscopy, and we're not biased to any other thing that might lead us to infer incorrectly that that mergers are happening in where the highest number densities of galaxies are. All right, but again, we're still cheating. We're still not using the ground truth. We still don't have a method of which it's ground truth only, and we're still not using a method which is entirely non-subjective. We're still basing it on human knowledge. It'd be really great if we had a model which did all of this for us without including any human knowledge and any subjectivity. So just training based on simulations and applying to observations all on its own. But in order for this to work, it seems like some more data, more ancillary information will be needed, right? So if I take so what I'm showing you here is just a plot as a function of the sensitivity and specificity of the model, which is just the completeness, the rate at which I'm correctly classifying mergers, and the rate at which I'm correctly classifying non-mergers. And on the y-axis, I'm showing you the posterior purity of the model in terms of mergers, right? So that is the probability that a galaxy is a merger, given that it was classified as positive. And this is extraordinarily sensitive to the initial or to the intrinsic fraction of mergers in the real universe. So that is what is being shown in each of these curves. If the fraction of mergers in the real universe is 50%, then we're doing pretty well. The fraction of mergers in the real universe is not 50%. 1 in every 2 galaxies in the universe is not merging at a mass ratio of 0.1 or greater. So it's more realistically in the range of 1 to 5%. And what that tells us is that our posterior purity, if we are at 90% accuracy, the model is at 90% accuracy, and then our posterior purity is expected to be somewhere between 8 and 37% or 34%. That's very bad, right? Because if you're for any sort of scientific study, such as the star formation rates or AGN activity, you can't tolerate that level of impurity. So the question that I wanted to answer was, can some ancillary information be used to get us further along on this accuracy plot, so we can get to higher posterior purities? And that ancillary information would be the stellar kinematics, because while gas kinematics are often more accurate, the stellar kinematics exist for all galaxies. Some galaxies do not have gas, so you would want to use something which all galaxies have, and all galaxies have stellar kinematics, so long as they have stars. Right? And so the rationale for using stellar kinematics in tandem with imaging is that sometimes these two pieces of information can tell different stories about the merger state of a galaxy, right? So what I'm showing you on the left-hand side is a post-merger, exactly at coalescence. It's a mass ratio of 4 in 10. So 40% of the galaxy, its companion was 40% of the mass of the primary. You would not infer based on this image that this galaxy was a post-merger. There's nothing in that image that would, is informative. Whereas in the stellar kinematics, it's very clear, right? Normally, a normal stellar kinematic profile would include, some axis of axis symmetry, around which if you rotated it, you would get, a symmetric result, right? But what we're seeing here is a very strong asymmetric asymmetries in the kinematics of this galaxy, and that is clear evidence of a merger. So if this is true of all galaxies which don't, if this was true of all galaxies which don't exhibit merger features or merging galaxies which don't exhibit merger features in their photometry, then you would greatly improve your completeness and purity of post-mergers by including the kinematics. Right? And also, we live in an era of IFU surveys. And we have, of course, Khalifa, Sami, Manga, and forthcoming surveys like Hector, which will very soon give us 50 orders of 10,000s, tens of thousands, 50,000 IFU cubes for local galaxies in the local universe. So here are images of our control galaxies. These are non-merger galaxies that we identified as controls for our post-merger galaxies. So here are images of the post-merger galaxies. So you can see that they all exhibit, or many of them exhibit, very strong features of post-mergers. They're visually different. Here are the control stellar kinematic maps. So we have, many of them have this very characteristic symmetry, some not so much, but nonetheless, we hope that by combining both of the pieces of information together, that it will be able to identify ones that are bona fide post-mergers. And so, but as you see, these are galaxies that are post-mergers, and these are their stellar kinematics. Many more, there's a significantly greater fraction of these galaxies, the post-merger galaxies, that exhibit highly asymmetric features in their stellar kinematics. So the design of the experiment is that we take a model, a ResNet in this case, and we train it on photometry. We take a ResNet and we train it on kinematics to identify post-mergers and non-mergers and post-mergers. And we train a model which also incorporates both of these pieces of information together, both using a two-channel and sort of a dual component CNN. We just find that the dual component CNN does a little bit better. Yeah, so by comparing these, we can assess what is gained by incorporating this stellar kinematic information. The stellar kinematic information is shown here, photometry is shown here, and the combined data is shown here. Well, you don't get anything actually. So by incorporating the stellar kinematic information, you get no gain in terms of purity. You maybe get 1% gain in terms of F1 score. We're going from 93% to 94%. You may get a little bit of a gain in terms of completeness, but you get no gain in terms of purity compared to imaging alone. So the stellar kinematics really offers nothing over top of regular photometry. And the worst thing about that, and that is in the idealized case. We're using idealized images. We're not using images that have been processed to look like manga maps that have all the noise and all these other features that would pollute the data. In the degradation of IFU kinematics compared to photometry is much greater. So we're doing the best we possibly would with kinematics, and by incorporating all these noise features, you would do much worse. So really, this is the limit of how well you would do with it by including the kinematics. And so this is what you're showing here again, the posterior purity, as before, the probability the galaxy is a post-merger based on the fact that the model said it was positive for the different, for each different model as a function of the intrinsic post-merger fraction. That was that 1%, 5%, 10% in the previous slide. And we see that the photometry and the combined model overlap exactly. So you're not gaining anything by incorporating stellar kinematics into the model. All right. So how sensitive is this to the time since the merger happened, right? So we can then take images of galaxies that are after their mergers and assess how long after the merger we still see the relics of the merger itself. right? So we have here, axis is showing you the T post-merger, the time since coalescence. So it's starting at 0 and then extending up to essentially the age of the universe if the galaxy was at very high redshift. So of course, at T post-merger equals 0, which is what the model was trained on, this blue part here, then we do very well, between 90 to 94% based on any of these particular data sets. But as we go to just 1 gigayear after the merger, we're down to 30%. Now only 30% of the galaxies are positively classified as post-mergers. And after 2 gigayears, almost nothing, right? So, not looking good, looking a little bit bleak. But what if we reframe this problem? We've wasted all of this data. Look at all this data here that we've only trained on this year. We have all of this data for which we have like float numbers, which correspond to how long each galaxy has been since its most recent merger, right? Since the time post-merger. But we're ignoring that data in the training. So why not reframe the problem? Instead of treating this as a classification where we're trying to identify whether the galaxy is a post-merger or not, why not treat it as a regression where we try to predict what the time since the most recent merger was, and then exploit all of that data? So that is what we did. So here on the y-axis, I'm showing you the predicted time since merger, and on the x-axis, I'm showing the true time since merger. And this is for the kinematics, the photometry, and the combined model. And what you see is that up to about 4 gigayears, you do extraordinarily well in terms of predicting when the most recent merger happened. Now that's a bit frightening, actually, because most of the dynamical features of the mergers should have relaxed within 1 to 2 gigayears. So it's very strange. We see this, like the longevity of your ability to identify a post-merger galaxy and its time since merger. This is quite unique because what this implies is the merger itself is the impetus for some major structural change in the galaxy, which that makes sense, but then disappears after a few gigayears, and then you have some other feature which acts as a ladder to that point. Some thing that is happening regularly in time, which allows you to go back to that point of major structural change. So again, sort of shown here. Here, we're looking at the same plot, T post-merger in true versus T post-merger predicted. And each of these lines corresponds to the individual merger history of a single galaxy. So starting at point 0, that is when the galaxy just merged, and then we're making predictions along the entire descendant history of that galaxy. So prediction here would correspond to something that is 8 gigayears after the merger, right? And whereas here would be right at the point of the merger. And what we see is that the scatter in this relation, is very strongly correlated with the mass ratio of the merger, which is to be expected because lower mass ratio mergers will produce less of a gravitational response in the primary galaxy. So that's why we get this sort of over prediction at low. So why we get this over prediction at low true T post merger in this regime. Whereas some galaxies, such as these very, very high mass ratio galaxies, you can predict the time since post-merger up to 8 gigayears after the merger. But that is astonishingly strange. Yes, I still don't understand, and I still don't understand this. That's why this work isn't published. It could be because the acquisition of satellites, basically the model is learning to count up how many satellites occur in the image, because the acquisition of satellites is essentially a stochastic process with time. But using activation maps does not reveal using certain ways of identifying what the model is exploiting in order to make it and inform the regression. It doesn't seem to be anything particularly obvious, so it's a bit strange, but nonetheless very interesting because it does imply that you have this major structural change and then a corresponding ladder which bridges you to the current time. All right. So we can go even further than just predicting one value, right? So we can characterize the assembly histories of galaxies using several summary statistics, right? So we can look at the mean merger time, mean merger mass ratio, last major merger mass, last major merger time, and the ex situ mass fraction of the galaxy. And then we can use certain observables, such as these, just basic observable characteristics of galaxies. We can train an invertible neural network. In this case, it's a CINN. We won't get into the details because I'm running out of time. But you can use this to predict things like the exigent, all of these properties just based on this very basic set of observables, right? And for some of these properties, particularly the exigent stellar mass fraction, is very well predicted with very good, very small scatter. So it's quite powerful. But these are all essentially, those properties were all essentially non-lossless compressions of the data. So it would be much more ideal if we could just use the entire maps themselves, the images themselves, instead of some very compressed summary statistics of the information encoded in those images. So why not just use the images themselves as a whole? And so that is what we're doing now. And we're doing this using a data set that I made of 750,000 images of galaxies from the TNG 50 and TNG 100 simulation between redshifts 0.1 and 0.4, using this very detailed forward modeling with SCRT, this radiative transfer process. And these are just some basic characteristics. I won't go into the details, but nonetheless, you now have an enormous data set of galaxies, not only with idealized images, but also insertions into the real HSC survey. Okay. And the model of choice for this is a contrastive model, right? Because what we seek is representations of galaxies, but ideally ones that do not require any labeling, because labeling is expensive. We saw that with Galaxy Zoo. It took a lot of time in order to collate and collect all those Galaxy Zoo votes. Instead, what we can do is we can learn meaningful representations of galaxy morphologies without labels, just by using models such as this. So in a contrastive model, you can think of it sort of as with Netflix, right? You log into Netflix for the first time. You have three movies that it asks you to pick, and then each of those movies will have some representation vector associated with it. And then you end up in some very discrete part of the representation space of recommendations that it's very difficult to leave after you pick those movies, right? You might find it difficult. And so this is just like that. So because what is happening here is that the model is putting images together, which are intrinsically similar, and pushing images apart, which are intrinsically different. And so it's doing this grouping, these groupings of data all on its own, without any labels. So it's very powerful in this respect. And what you end up with is these representation vectors, which are meaningful. And here's some evidence of this. So we train a model which uses both TNG and HSC galaxies together. So these are real HSC galaxies. And these are the nearest neighbors in that Cartesian representation space. So just like I showed you before, where I picked a dust lane galaxy and I picked 16 other galaxies with dust lanes, for each one of these galaxies, I can find its analog in representation space among the TNG galaxies. Now, this is also very powerful because it allows you to find analogs for which you know the intrinsically unobservable properties of those galaxies. Right? You know the assembly histories of this galaxy, and then you can infer what the assembly histories of these galaxies are based on that mapping between them. And you can see that they're very similar. It's quite beautiful how similar they are in terms of morphology. So all this is to say that we're starting to do a very good job of characterizing not only classifying galaxies here in the post-merger phase and characterizing, because all of the action is happening here, because not only are you having these bursts of star formation, as I mentioned, you have this enhancement of star formation, but you're having this this is also where you're seeing the quenching of galaxies as a result of those starbursts. You have quasar activity and morphological change, transformation from rotational support to dynamical support, or to dispersion support. All of this stuff is happening in the post-merger phase. So we're getting away from just using forecasts, and we're actually starting to get to the assembly histories of galaxies using this combination of forward modeling, hydrodynamical simulations, and deep learning. And so I think that I'll leave you with my summary slide. Thank you all for listening.
All right, thank you, Connor. Do we have any questions from the audience? Yeah.
Yeah, well, just a quick question on something you mentioned. So the main limiting factor, am I correct in saying the main limiting factor in your works right now is the precision of the observations of galaxies that we have? Since you've had to downgrade the resolution of your model of your modeled galaxies.
Yeah, sure, yeah.
So that would be the main.
You could say that, yeah.
Yeah.
I mean, you never want to bang the observations, right? So
No,
you never
no.
want to bash the observations because that's, you know, it's actually not a very difficult process to degrade the images once you already have the rate of transfer and stuff. But yeah, I mean, better observations to compare with are always better. If you had JWST images of every galaxy, and then you would, I mean, ideally, you would have Gaia for every galaxy, and then you'd be able to exactly piece apart its assembly history, right? But we only have Gaia for our galaxy and maybe Andromeda.
No.
So we have to do with what we have. Yeah.
Yeah, so I guess it's very interesting, very good work. And I was wondering, like, is there also the kind of reverse direction, whereas, you know, like, simulation is always wrong. It's a better way to, obviously now we're working on simulations to try to know stuff about the universe. But it's also where we use these negative representations to not actually understand something about the universe, not until the simulation or how it's very different.
Yeah, so there are definitely efforts in this front because, you know, of course, these simulations include subgrid models, which are not physical, right? They're completely empirical. We don't know, we don't have good constraints based on observations, how the accretion rate onto a black hole in a particular configuration codes exactly to AGN activity and what mode of AGN activity, whether it's leads to a blowout, where most of the energy is in kinetic energy, or whether it's mostly heating. So these are all prescriptions that are used in the simulations which don't have very good observational basis, but they're used because they work. They reproduce some observable, such as the stellar mass function or the halo mass function. Yeah, I mean, there are efforts on the front of, you know, using what is sort of called constrained simulations, where you have you try to optimize your subgrid physics based on not only on these very crude scaling relations, such as the stellar mass function, but also on the galaxy morphologies themselves. So there are efforts in this area, yeah. But I think does that answer your question?
Yeah,